All right, we're going to talk about induced current, and this is current that is created by the presence of a changing magnetic field. So I'm going to just start out by looking at a magnetic field where we have it coming out of the page here, as you can see. And I'm going to draw a metal bar here. And this metal bar, as we know, because it's metal, has charges that can move around it, right? So we're going to give this bar a velocity v. And if we use our right-hand rule, now this is right-hand rule for moving charges, we're going to use our velocity is v, that's our thumb. And then our fingers are the magnetic field, so they're pointing out of the page, right? And our palm gives us the direction of the force, so the force on the charges due to this magnetic field is pointing downwards. So we can imagine that there's this force on the bar, and it's moving all of the positive charges to this end, because remember our right-hand rule applies to positive charges, and the negative charges on this end. And I know you're sitting here going, but how is this going to be possible when a metal bar doesn't allow for an internal electric field to be present? Well, we can actually have a electric field inside of a metal object if it's in a magnetic field. So this is called the Hall effect, but that's not the most important part of this at this moment. What I'm going to do is I'm going to take and put this metal bar on a couple of rails. Okay, so as it's moving along, now we have a loop, in essence, going from the metal bar around this rail. Okay, and we're going to say that these charges can flow along here. And what's going to happen is, exactly the way I drew it, we're going to have a current now going along this metal rail. Now, we know that when we have a magnetic field, a current, and it's flowing in a loop, that creates a magnetic field. So we're going to use our third right-hand rule. And our third right-hand rule is similar to our first one. In our first one, we used our thumb for the wire, right? And we could say that using our fingers, we could figure out what the magnetic field around a wire is. We could do something similar here. The end result is that on the bottom, the magnetic field will be going, due to this current, is going to be going into the page. Same thing on the side, and same thing here on this top one. If we continue on the outside, we're going to see a magnetic field that's pointing out of the page. But what we're concerned about is what's going on inside the loop. And inside the loop, we have a net magnetic field going into the page. This is where the third right-hand rule comes in. The third right-hand rule says, it's kind of the flip of the first right-hand rule, where if we take and we have a current that's moving in a loop, we can bend our fingers around the loop. In this case, our fingers are going to go clockwise, right? So they're going to go in the direction of this current. And our thumb will then point in the direction of the magnetic field. So the magnetic field is going to be pointing into the loop here. And this is our induced magnetic field, and this is our induced current. And it's caused by the fact that we have motion from a metal object in a magnetic field. Okay? So we can think about this. It's called motional EMF. And EMF stands for electromotive force, because something is moving. So it's kind of redundant to call it motional EMF, but electromotive force. And the big reason we use an electromotive force is because that's what we generally get out of something like a motor, right? A motor is going to move. It uses a magnetic field to actually create an electric current. So that's where the EMF comes from. It has the same units as volts. So a voltage source, or a battery, we usually call V, right? And that provides us energy through chemical means, and electromotive force provides energy through a motion in a magnetic field. Okay, so they both have the units of volts. All right. So let's think about the fact that we've got this area that's increasing, okay? And what's going to happen is we have a magnetic flux. I'm going to change back to black here. We have a magnetic flux just like we had an electric flux. And our magnetic flux is equal to the dot product of the magnetic field with the area. Of course, we remember that an area vector is defined by the area itself times the normal vector that points perpendicular to the plane of the loop. Okay? So if we want to think about how to create an EMF, which I'm going to write as squiggle E, that EMF is going to be equal to the change in the magnetic flux over time. Now, if we think about our calculus, we're basically going to end up with a product here. We have to use our product rule because this means we could have a change in the magnetic field over time times area, plus we could also have a change in the area over time times the magnetic field. Usually we have one or the other. We don't usually have both, but you will see problems of each type. So keep in mind that we have to use our chain rule here. Okay? So, in this case, what's happening is we're not changing the magnetic field, we're changing the area. So this would be describing this scenario where we have this bar moving through the magnetic field. Okay. So let's think about how do we figure this out? So we figured out the quantity or the magnitude, right? But it gets a little bit difficult to figure out the direction all the time. So I'm going to step you through a few steps on how to do that. Let's start by imagining we have a metal loop, okay? And we have a magnet. The north end is here, the south end is here. And this magnet is moving upward towards this loop, right? Well, if we want to think about how our magnetic field works, we're basically, the magnetic field is coming this way out of our magnet, and then it's going to be coming back into the South Pole, right? So as we move this up, the density of the magnetic field increases over the area. Not all of the, when it's farther away, not all of it's going to be going through the loop. Some of it might bypass out of it, okay? So what's going to happen is as we move it up, more of those field lines are going to get captured in that loop. Okay, so the first thing is we're going to figure out, well, what's the direction of our field? In this case, the direction of our field is pointing upward, right? So that's their direction. The second step is, how is it changing? Is it increasing? Or is it decreasing? If it's increasing, we create a delta B, and it's going to be pointing in the same direction as the magnetic field. Okay, so the north field points up, and it's moving into the loop, so that means that the magnetic field is becoming more dense in the loop, so it's increasing. So our arrow points in the same way. Now, we're going to look at something that's going to oppose the change. So the big point of all this is magnetic fields don't like change, okay? So what's happening is when that current is being induced, it's trying to oppose the change in the magnetic field. If the magnetic field is increasing, that induced current is going to decrease. And if we look back above, we can kind of see what's happening there, right? We have the bar moving to the right in a magnetic field that's pointing out of the page. And what it does is it induces a current that spirals around that loop, and that spiral current creates a magnetic field into the page. So it's trying to oppose the increase in the magnetic field by creating a magnetic field in the opposite direction of the one that's present. So how we want to oppose the change, so the opposed change is going to be pointing in the opposite direction as our delta B, okay? So since delta B is pointing up in the same direction as a field, the opposed, the opposition, or the inducted current is going to try to create a field opposite that, okay? And that means it's pointing down. So if we assume that this loop here is horizontal and this is the front and this is the back, okay, I'm going to point my finger down because that's the direction that's opposite, and my fingers are going to curl around to the right. So it's going to go clockwise from back to front, and that's the direction of the induced current. And that's going to create a magnetic field to oppose the magnetic field that's increasing from the magnet moving towards the ring. Okay, so the fourth step is find the induced current based off the direction of opposition. Okay, so that's the last and final step to finding an induced current. Okay, we can do the same thing. Let's try imagining the opposite scenario. What if we have a ring, okay, and now we've got a south pole going into it, okay? The south pole is pointing down, right? So the first step is the field is pointing down. The second step is to figure out the direction of change. So if we've got this magnet, let's move it in the opposite direction as before. So it's pointing down, but we're moving away from the loop, so it's decreasing. So there's our original field, and it's decreasing, and when something is decreasing, that means it's pointing in the opposite direction of the field. So this is kind of our, when we talk about changing position, but then we have a decreasing velocity, that means it's kind of slowing down and pointing. Our velocity vector points the opposite direction from our position vector. So it's decreasing, but since it's moving down, that means that our arrow is going to point up to indicate that it's decreasing. We want to oppose the change. So to oppose this change, we want to have something that's the opposite direction of that. So our induced magnetic field is going to point downward. And then then we use our right-hand rule. My thumb is pointing down, right? And what's going to happen is my fingers are going to curl around this direction towards the back. So this is the back and this is the front of the loop. It's going to curl from back to front, so we have a clockwise current. So use your right-hand rule to find your induced current, and that will be, in this situation, clockwise if we're looking at the loop from the top. So you also have to take into consideration which direction you're looking at the loop from. So that is basically how you find the direction of the induced current, and then if you want to find the magnitude, you're going to use this equation right here.